Today, we're going to take a look at something that really is kind of near and dear to my heart. That is the protocol of TCP over IP. You might see there with the certified ethical hacking and Wireshark and perhaps a couple of others that I do participate in security measures. But for me, the core of that understanding of security has always been built around the idea of how the TCP over IP protocol operates. So if we move to the next slide and take a look at that, what we're going to talk about is what is the importance of this information, a little bit of basics about what TCP over IP is. Going a little bit deeper, we'll look at a few protocols, IP, TCP, and UDP, just a little bit deeper. And believe you me when I say TCP by itself is probably the most complex protocol that you can imagine. We're not going to do much more than just scratch the surface. We will take a look at other protocols, and in fact, one of the things is that we will do is define the word protocol. We'll also take a look at something else that is very important within this concept, and that's how information moves from one system to the other. That's found in the basics of routing. We'll touch on subnetting, which is a topic that allows for the appropriate distribution of addressing in an IP version 4 architecture versus the IP version 6 architecture that we will touch on. We'll then follow up with some questions and answers. So if you do have a question, I hope I have an answer for that at the appropriate time. So that's just a brief look at our overview. And as we continue into this material, by moving to the next slide.
Yes, sir, we'll do, Lane. And just one more thing to add, everyone, if you do not mind adding those questions to the question and answer chat box. There's actually two different boxes. One is for chat, one is for question and answer. All questions, please address them within the question and answer box. Thank you.
And thank you for that, Jamie. We ask our first question is, why is this important? And what we identify in this is the ability of one system, a machine, a computer, to talk to another machine, another computer, or really for that matter, a large number of other devices that we see that are apparent in the world now, telephones, cameras, printers, and as we move into the Internet of Things, almost anything that you can imagine can be attached to this architecture and managed and controlled via the protocol of TCP over IP. Hence, that's almost universal or ubiquitous use within this overall structure. And of course, without understanding that information, we simply cannot design our networks of the future. We cannot operate and manage those networks of the future, nor can we troubleshoot those resources. So all of those are three very good reasons why we would like to function or know a little bit more about this protocol. So let's go ahead and jump in by moving to the next slide, and that is, what is TCP over IP? Well, if we look at it just by itself, it is a singular protocol grouped together on top of another protocol. The TCP portion of that protocol allows me to determine how two machines communicate to each other. But it doesn't tell us how we get from here to there. That's the responsibility of the IP protocol to deliver our message from one system to another system. And the term protocol, it does come from, if you've heard it before, diplomats use a particular protocol. It's a standardized set of rules within communication to allow us to communicate with clarity and appropriateness. And that is a key element for diplomacy, and that's a key element in this environment. One of the things that I would like for you to take from this class is that IP is rather simple. The complexity of IP comes from its ability to create a universal protocol that's used to connect all of the machines in the world together to create what we call the big I internet. And that internet, well, we do know it spans the globe. And as we've seen with the Internet of Things, it's not stopping there. Now, there are a number of other protocols. There are hundreds of protocols. Anything that we do to establish communication from one system to another system is considered a protocol. They can be underlying protocols like IP is. They can support the machine-to-machine communications like TCP and UDP, or they can be independent like DNS. How do I locate another machine in the internet? That would be through the domain name system. And that too is a way of doing things, a standardized set of rules. So it too is a protocol. SMTP is one of the email protocols in the internet. So if you're doing email, you're likely to be doing that at SMTP, or Simple Mail Transfer Protocol. There are, of course, other email protocols that do exist, or email services. And some of the things that we're looking at now are at the service level, the reason that these underlying protocols exist. We also skipped over briefly ICMP, and ICMP stands for Internet Control Messaging Protocol. And that one is network diagnostics. And you may know it as the protocol that allows you to ping one machine against another machine. Is that machine up and running? But it is much deeper than that. It allows us to identify what's going on in our network and how we're allowing communication to occur. And of course, the biggest and most robust protocol is HTTP, that protocol that runs the internet, the browser functionality that we're all familiar with. And of course, in this day and age, we cannot look at networking without identifying or understanding some of the security needs. And the protocol of TLS secures communications like HTTP so that we can continue to do web browsing, but we can do so securely. And of course, there is a much, much longer list of other protocols that do exist. Just take a look at the internet and you'll see them. FTP, a routing protocol known as RIP, post office protocol, finger, the list goes on and on and on. So our next slide will take us one step deeper into this idea by giving us a very nice structured approach. And one of the things that when we look at networking, we always have a tendency to talk about a layered model. But in this particular image, you are looking at the layered model that TCP over IP uses. It has its own distinct functionality, and it begins at the network access layer. You see that at the bottom. This is where we identify the physical interface and the protocols associated to the physical interface, Ethernet, Wi-Fi, point-to-point protocol, as well as others. And some come and some go as things change in this organization. Now, briefly, one of the other things that we look at is, and you see a couple of numbers in that network access layer, 0806 and 0800. They are values found within that area that tell us what type of protocol we're using and where to pass it up the protocol stack, so that at the appropriate information, if a device sees a 0806, they send it to the ARP process. If the same device sees a 0800, they send it to the IP version 4 process. And it is that idea that forms the function of a protocol, the definition of these numbers and their meaning across all of the platforms that are structured within this. You see another example of that as we rise above the IP version 4 level. They show us 5 different paths that we could theoretically take. Now, 3 of them kind of terminate at the IP level, and there's reasons for that. And we won't go deep into that, but we will explore it as we look at the 2 that are above IP with the values of 6 and 17. That would be TCP and UDP. But let's go back into IP for one more moment here. If you'll remember, I mentioned the IP level as being responsible for the determination of how I get from one machine to another machine. And that is through the use of routing protocols. And we see 2 routing protocols mentioned here. One is EIGRP. That one has the value of 88. That one is a Cisco protocol that is used to identify and find where a machine is located. The acronym stands for Enhanced Interior Gateway Routing Protocol. 89 is another routing protocol. So we don't just have one functionality that tells us how we get from one system to another. We can make choices or decisions on what protocols we like to use to identify the best way to get from here to there. The protocol with the value of 89 is OSPF, and that's open, shortest path first. The open indicates it's an open standard, and the method by which it determines the best path is one known as shortest path first. And we see our good friend ICMP, our network diagnostics, for IP at the value of 0, 1. We also build on that structure with the 2 other values, and these go up into another category known as the transport layer. And the transport layer defines how we move traffic from one system to another. We can either do so in a connection-oriented fashion, that's TCP, and connection-oriented simply means that when I send something to that machine, I expect that machine to send me a response back, acknowledging that it received what I sent to it. And that is entirely appropriate if we want to maintain communications and ensure that those communications are received, processed, and managed correctly. But occasionally in this environment, there are needs to just send information and forget about it once it's been sent. And that is the example that we see with UDP, User Datagram Protocol. And I may not have defined TCP Transmission Control Protocol. We see a couple of protocols associated to UDP. They're probably not as popular as some of the other ones, nor as apparent, but the way your machine gets an IP address and other information necessary to become a member of the network, that's DHCP. TFTP is known as Trivial File Transfer Protocol, and it does move a file from one system to the other, very small files, commonly router configurations and things of that nature. Of even more complexity is the SNMP, Simple Network Management Protocol. And the only reason that it gets the designation as being simple is because it sits on the UDP protocol stack. Otherwise, it is probably one of the more complex protocols that you would come across in this environment. And if we think about that for a second, you have a singular management protocol that manages everything that potentially has an Ethernet interface. That's a wide range of vendors, a wide range of devices, and all of them can be managed through this singular protocol. That protocol is extraordinarily powerful, but simple it is not. Now, an older routing protocol, a peer of EIGRP or OSPF, is that of RIP. I say it's a peer But it really isn't. It's a little bit older, and so it's structured just a little bit differently. It was the earliest routing protocol, and it does show its age, and that is Routing Information Protocol, or RIP. Now, I did jump over the TCP protocols because in general, they're a little bit easier to understand. And Telnet is a command line communication between two systems. FTP, file transfer, a methodology to move information from one system to another. SMTP, the email protocol. HTTP, the core protocol of the internet or web browsers. And with those four protocols, it should be noted that we rarely use them any longer, mainly because not one of those four protocols are secure. They send information in clear text, passwords in clear text, and things of that nature, so that these protocols have been augmented or replaced by more secure iterations of protocols. Another one smack dab in the middle is DNS, and DNS has a number of responsibilities. Hence, you see one referencing TCP and the other UDP. Our most common use of the DNS protocol is a DNS query. What is the IP address of www.google.com? I would ask DNS that, and that would make use of the UDP protocol, because the complexity of setting up a communications between devices via the TCP protocol is very demanding on the systems. And I really only have a simple question to ask. And so that's another reason that we might use the UDP protocol stack. However, if I'm moving the content of my DNS server to a backup DNS server, this is a function known as a zone transfer, I would prefer to have some understanding that when the information leaves, it's going to arrive at the other system intact, with the integrity in place and things of that nature. And TCP provides that functionality. So even though we have the same protocol, its different responsibilities may make use of those resources. But if there's one thing that I would like everyone to take from this particular slide, and that is, this is the structure of a packet. We see a header at the bottom. We see just above that the IP header. We see a transport layer header, and then we see the content or the information within the delivery of that information. And this is the protocol or standard by which we agree to those particular exchanges. Our next slide will allow us to kind of take a look at IP portion of this. And it is the protocol that carries the data, if you will. Version 4 is the popular variation of this. There is a version 6. It suffers, the version 4 rather, suffers from a few things. And that is basically its 32-bit address. Now, 2 to the 32nd power. And because an IP address is a series of either zeros and ones, we can determine the total number of potential IP addresses by that simple calculation of 2 to the 32nd power. That's 4.3 billion. And if you had a calculator, you could do that, or you can memorize it. And there are a number of problems with the distribution model. 4.3 billion may have been enough, but the way they distributed the IP addresses originally created some problems in that distribution. So we are well aware that, you know, we're running out of IP version 4 addresses, and that is the reason to move to IP version 6. But there's also one other slight thing to note, and that is the US of A invented the internet and these protocols. And so we actually gobbled up all the good numbers before we shared it with the rest of the world. So outside of the US, you're a lot more likely to see the use of IP version 6, but inside the US, Canada, it is still the predominant protocol. And the functionality of the IP address is to provide that routability. This is that top point that they make. And that means, and here's where we do get into a little bit of the complexity of the IP number. And that is, when I look at an IP address, I expect to see some bits representing the network, and those would be the leftmost bits, and some bits representing the host, a member of that network and its numeric value, and that would be the rightmost bits. And somewhere in the middle, or wherever we want them to meet, is the net mask that tells me what bits are network bits and what bits are host bits. And that does create a little bit of complication, as we'll see on the next page, because what we look at when we're seeing this information. And so our next slide will take us into that briefly. This is not anything I want to explore with you. I'm going to point out that this is part of the IP version 4 header, and it is accurate. It shows that there's an IP version number of 4. There is an IP header length. There is 6 bits used for differentiated services, and that is quality of service within the internet, explicit congestion notification, total IP length, ID flags and fragmentation, time to live, protocol, and you'll remember that that points to the next thing. So what I can tell you about this is the protocol that it follows this is an ICMP protocol. A checksum to protect the integrity of this header, and source and destination IP addresses. It might be worth noting, since I did go a little bit more into this slide, that those values are represented in hexadecimal. And as a brief aside, what I might say is that if you are going to attempt to understand networking, it's going to benefit you a great deal to spend a few minutes working on your understanding of base 10, base 16, which is hexadecimal, that's what we're looking at here, as well as base 2 understandings. That's just a hint. I'll not go any deeper than that, and we'll move on beyond this particular page. So our next slide will tell us just a little bit about TCP. And TCP is, as I mentioned before, a connection-oriented protocol. What this means in this context is that before I exchange any information between the client, that is the party wishing to set up a communication, and the server, I will establish a session. There's this thing called a 3-way TCP handshake that tells us exactly how this session is established and what the ramifications of that are. And what we would see in this particular model would allow us to identify the flow control, what's being sent, and sending back acknowledgments to the other side. When working in this particular model, what we have the functionality of doing is a full duplex communication. And if you want to think of this as a phone call, that would be very appropriate. It is connection oriented. The call was set up. You can speak, either party can speak. It provides a reliable communication. Now, in the TCP over IP, it's a sequence value and acknowledgement numbers. You also have the ability for each side to determine how much information needs to be sent at one given point in time. And it is a one-to-one communication, hence the client server functionality. And if we're talking to the various resources, the numbers that I skipped over in the other one are the ones that identify applications. 23 for Telnet, 53 for DNS. They merely tell me how to communicate to the upstream machine and identify what's going on those particular systems. And continuing on towards our next slide, we see the TCP header layout. And once again, just some brief references here. And that is, when talking from one machine to another, it is very common for us to establish our source and destination ports. It may make a lot of sense to you when you say, oh, when I have this system with this IP address talking to that system, I can look at the IP header and see the source and destination pairs. But we also share that same idea in this particular header. And that one is a truly fascinating topic, because I do believe that once you make that clear in your head, then you have a good understanding of what this protocol and the overall functionality of it provide. But I also made brief mention about a little bit of the complexity of TCP in and of itself, and the sequence and acknowledgement numbers would contain a little bit of that functionality. They also have a little bit further down session flags that determine exactly how we're communicating to the other side, and they give the other side hints about what that communication might be. I mentioned the flow control, and the designation of the flow control is found in the window size. Once again, to protect the integrity of the information being delivered, they make use of a checksum. And an older remainder of something else from the past is an urgent pointer. Well, like I said, that's the past, and so we'll leave that in the past. But as we move to our next slide, we'll take a look at UDP and some of the characteristics of UDP. Now, one of the reasons I made kind of a big deal about the connection-oriented is that is the biggest difference between TCP and UDP. UDP is connectionless. And all that simply means is that there was no establishment of the call functionality before sending the packet. I just simply, as a sender or a client, will send the packet to the server. The server will not tell me whether or not they've received it. It's up to the upper layer protocol to handle things like that. It is unreliable and provides a best effort solution, but as in the example of UDP, your system knows that I sent this out on UDP, and so I'm going to wait a little while, and if I don't hear back from the other system in a reasonable time, I'll send it again. So the functionality of best effort can be obtained by using something like that, letting something else handle the potential problems rather than making the systems talk back and forth. Now, just like TCP, though, there is the port numbers that identify the application functionality out of those things. It's simpler and it's faster, and it makes sense in a number of different situations. Voice over IP is one of the biggest systems that does use UDP when a voice call is in place. And there are a handful of reasons for this. First is that voice is real-time communications. And me sending a lost packet a little bit later in a voice communications makes no sense. I can resend, but it doesn't fit in anywhere. I've already spoken those words, and they only make context in that sense. Also, I can tell you that a voice call consumes 86.7 kilobits per second if the protocol is G.711 and you're using a 20 millisecond sample. And that means I can't dictate things like I can in TCP, and that is I'll make a deal with the network and say, look, I'll use less bandwidth right now in exchange for more bandwidth later. With UDP, you want what you're using. So voice and video are both good examples of what UDP provides for its communications. An example of the UDP header on the next slide identifies that particular type of functionality. So as we move to that next slide, we see the UDP header, and this time they show us a little bit more of the functionality of this. We see the Ethernet header at the top of the screen. That's 14 bytes, and we could dig deeper into that. We saw a brief reference to the IP header, and we saw the 20 byte size, which is common for the IP header, but it can expand up to 60 bytes. We also see that that's followed by a UDP header. Now this UDP header is pretty doggone small. It is 8 bytes in length. It contains the source and destination ports. Those are 2 bytes apiece. It contains a length field. The length field defines the length of the header plus the contents of the payload behind that. And then a checksum that is optional. And the checksum is optional. The sender of this gets to determine whether they enable the checksum or not. The receiver merely looks at that field. If the checksum is there, they'll calculate it and determine the integrity. If it's not, then they have nothing to do. I will also give you one more little hint right here, and that is the destination port is one we've seen before. And in order to understand that, we would have to multiply 3 times 16 and then add 5 to that, because the 35 that we're looking at is once again hexadecimal reference point, and 3 times 16 should be 48, plus 5 is 53. The very end of the information is a frame check sequence, and that one provides protection for the Ethernet header. So everything that we do, we try and attempt to ensure that there is accurate delivery by specifying a value and then doing the calculation on the receiving side to make sure that that information was sent correctly. Our next slide will take us a little bit more into some of the other protocols, and you see those listed here. We've talked of some of these. In fact, all the way down to the one identified as ARP, we've referenced. And ARP is a protocol that allows the Ethernet information, that is a MAC address, to also coordinate with IP so that those two addresses can communicate with each other. ARP is Address Resolution Protocol, and it's a system wherein you know the IP address that you want to talk to, and you learn the MAC address. The MAC address, and we would talk much more about that in Network Fundamentals, is an address for local communications. It's used within a local area network. I made mention of voice over IP. The functionality of a voice communication is known as a real-time transmission protocol, which gets the interesting acronym of RTP. Real-time is hyphenated, hence the fact that it's not RTTP, but rather just simply RTP. And the ellipsis, of course, indicates that there are a large number of other protocols, but we'll leave those for a later time. So our next slide continues us on in this, and that is, how do we know how to get from one computer to another computer across something that looks like this? Well, that's our routing protocols. And if we think about these as being telephone systems, those little squares within the LANs, you would know that there's a routing functionality for telephony. I dial a number and I get sent to a particular location and I terminate at that endpoint. The same thing is done for IP routing with one big exception. And that is that we deal with hosts at the endpoints and routers, which are those blue circular objects with the arrows pointing in and arrows pointing out, work together to create an understanding of the addressing. And by working together, we get a functionality that allows those routers to share the identification of the local area network that they're attached to. And within that, they share the information to their neighbors or peers. And the sharing process within the routing allows it to be dynamic. And another key characteristic of routing in the internet, hence the reason for voice over IP in a very large way, is that I can reroute around failure. So if one of these routers dies or the link dies or anything else in this network goes wrong, as long as I still have a router connected to that LAN, I can still get around that particular failure. And that key element is one of the reasons that we use voice over IP, because in a telephone call, you don't automatically reroute around failure. So we'll take our next couple of slides to take a look and see a little bit more about the routing functionality. And there is a decision process. If there's just a single way to send that information, then you select that route and you move that information. If there's multiple routes available, you look at the longest bit match and then the lowest metric. And what they're trying to say there is, what is the best way to get from here to there based upon the numeric value, but also this idea of a lowest metric. The metrics are the things that I'm going to compare the different ways of getting from one place to another by a means of the functionality of those protocols, the shortest path first. I want to pick the one that gets me from here to there, utilizing the least amount of resources. The metrics allow me to use that lowest metric. So when we route against most commonly that lowest metric. And of course, there can be situations in which there is no way to get from here to there. This is where ICMP comes in, and that router will deliver a message back to the requesting host that destination is unreachable, that you can't get there from here in those particular models. And as we continue looking at routing decisions on the next slide, we will look at what some of those metrics are. How do we determine what is the best strategy for getting from here to there? The RIP routing protocol would use something known as a hop count. How many routers do I have to go through to get from here to there? And that does at first blush seem like a reasonable thing. But as we began to expand our bandwidth, and bandwidth is a term used to identify how much flow between two routers that I might have, such as 10 megabits per second versus 100 megabits per second versus 1,000 bits per second, or 1,000 megabits per second, or 1 gigabit of communication. And of course, I would prefer to take a link that had a higher bandwidth from one side to the other. So the bandwidth metric is one that is used quite commonly. That is the core for the OSPF protocol. There are, however, other ways. I can just simply decide on my own administratively that I want the traffic to flow across those systems, an arbitrary path cost from an administrative standpoint. I can also look at other characteristics, but they are not as strong as the bandwidth in terms of functionality, a reliability metric, a delay metric, or a load or utilization metric. And we'll take an example at the utilization. In general, with routing, if you're sending all the traffic over one link, and then that link gets loaded or highly utilized, and then you begin sending traffic across another link, you're going to end up moving the utilization to that new link, and so you'll move back. And that does create a little bit of a problem. Now, there is a little bit more complexity in routing, and that is, I mentioned when something fails, we then have to determine how we continue sending traffic in the event of a failure. And we'll try and do so based upon these metrics, but we're going to have to, in some cases, calculate them again. And that does add a little bit more to our overall routing functionality. Another look at routing is found on the next slide, and this one is going to give us just a brief review and a reference point to a couple of other protocols. And what this asks is, what is the best way to get from LAN A to LAN B? And it gives us a couple of examples. And the most correct answer that we see in this is it depends upon the routing protocol in place. With RIP, we would use the hop counts, the shortest number of routers that we would go through. So we would go from that top router connected to LAN A directly to the one connected to LAN B. And that would be our 10 megabit per second circuit. So we're not taking into account the overall speed of the communications. OSPF might prefer the 1 gigabit per second links, EIGRP, the 155, and BGP, well, all bets are off when it comes to BGP. The RIP, OSPF, and EIGRP are all three examples of an interior gateway routing protocol, an IGRP. And that is, just simply put, a protocol used within your own network on your own routers that allow you to determine what the best way to communicate from one point to the other point might be, choosing that the specific protocols as well as other characteristics of those metrics. BGP is the protocol that allows us to communicate from one system to another. And when I say system, what I'm actually meaning is an entire network within the internet. That function is known as an autonomous system, and it's how we move traffic in the internet. And that is a much more complex protocol because, well, it is the routing protocol of the internet. And it's also the only example of an EGP, which is an exterior gateway protocol. But regardless of whether it is RIP or BGP or OSPF or EIGRP, it's still how is the best way to get from one location, one network in the internet to another, or one network in a architecture to another network. And our next slide moves us out of routing, which is kind of fun, by the way, and reminds us of this particular slide as we take a peek at that information. We identify some of the application layer ports. These would be the transport layer values that we saw earlier that once again tell us what process is above this on the machine so that we can send the information correctly to the above process. So moving into the next slide, we take a look at an IP address. And an IP address, because of various reasons, one of these, and you'll note that I'm going to mention the telephone company one more time. And there's a reason that I do mention telephony. I'm not a telephony person by any means, but if you were a network engineer or working on these protocols back in the day, the network that you would have identified with the most was the telephone network. And in the telephone network, they had devised a strategy for calling somebody worldwide by the use of a telephone number. And so when they decided that they were going to use addressing, they thought that it might be useful to talk about these addresses in a way that a person could understand. And work done in the telephone company told us that a person had the ability to learn and understand something at the range of about 6 values, 6 characters, or 6 numbers, if you will. And the reason I expanded that beyond numbers is if you have ever watched an old movie, you might see somebody share their telephone number by saying something like, well, you can reach me at Pennsylvania 65000. That one is a reference to a song, but it is a phone number. Your local CO, your central office, is the one known as Pennsylvania, or PE, whatever those numbers correlate to, 65000. And if you are in New York City and call that number, it will reach the Waldorf Astoria who purchased that number. So that's how people remembered a phone number, if you will. And they took all of those 32 bits and they broke them up into blocks of 8, known in networkies as an octet, known in other systems as a byte, perhaps. In fact, that's how they describe it, but you're much more likely to call that an octet in this situation. Now, based upon the net mask, there is a network ID or prefix. So when I'm routing, I'm looking first for the network of 172.16. And when I get into that network space, that's when I began looking for the host that is 200.1. Now, the entire address of that individual is 172.16, 200.1. But you can kind of imagine that you're in the right location. So now your concern is not those earlier bits as we were in the routing, but rather the host bits or the locally administered bits that tell us how to get to that unique network interface. Hence, only one device can have the IP address of 172.16, 200.1, but a lot of devices could have the locally administered 200.1 as long as they were in a different network. Say the network of 1.2.200.1, and that makes all the sense in the world. So that's a function of an IP address, is to understand where that break is. And there's where we get into a little complexity, as our next slide will attempt to elaborate on that idea just briefly. So our next slide shows us what we are doing with an IP address. And at the top, you truly see what an IP address is. This is what a machine would do when looking at it. This is how a machine would treat it. And if you are going to attempt to follow networking, you, number one, still need to know IP version 4 because it's still used widely and will continue to do so in the US. And I will say that after many, many years of teaching, I think that the best way to understand it is by looking at that top image. because once again, the reason that we break it down like this is so I can understand it. And that makes sense. I don't want to call you up and say, what's your IP address? And for you to begin reading off a string of ones and zeros, that is not going to make any sense to me. I will, however, understand 192.168.10.100, or the bottom entry for this. That is for people. For machines, we look at the top, and the breakdown of that is to take the 8 bits or the octet and translate that into 192, hence the need to know how to talk from decimal base 10 to base 2 communications, 168, 10.100. Our next slide will allow us to identify that while we can recognize that there is a networking function in the IP address and a host function, that if somebody gives me an IP address to work with for the reasons of making that information more fit my network structure just a little bit better, there is something known as a subnet. And the subnet, by far and away, is the most complicated thing that we're going to talk about today. So if you leave this going, well, gee, I didn't learn all that much about subnets, that's kind of okay. Now, here's what we want to do. In the beginning of addressing, there were 3 net masks that one could use. The net mask was a Class A, Class B, and Class C. And if you had a Class A network, you had one great big network of 16.7 million addresses. If you had a Class B network, you had a single network of 65,000 or so addresses. And if you had a Class C net mask, then you had a network of 254 devices and no more. Well, it turns out that networks don't all fit into those 3 categories. I have some networks that are about 500 devices. I have some networks that are 5 or 6 devices. And yet I would have to throw these big things at them in order for my network structure to exist. And so there became, within those 3 tiers of networking, the ability to subnet, or if you prefer, just simply break that space down into more usable functions. For example, if you had a Class B network, you could create any number of networks that you wanted, up to 65,536 networks. For example, you could get 2 networks of 32,768 devices, or 4 networks of 16,384, or 8 networks of 8,192. And you could subdivide that as you saw fit, but you did have some limitations. And our next slide will kind of give us an example of what those limitations are. And what I want you to look at is in the very corner of this, on the right-hand side, there's a pizza. And there are only so many ways that I can slice a pizza. And interestingly, I will end up with an even number of slices. I can cut it in half. If I go from one side to the other side, I can create fourths of that pizza. I can cut it a couple of more times and create eighths of the pizza. And that's a little bit like the idea of subnetting. That's why you see the pizza down there in the corner for that. And in this case, what they're talking about in that slice is creating its own network. So if you're doing something like this, you would first ask yourself, why am I subnetting? And that's to become much more efficient in terms of address distribution. You're not wasting addresses as much as you are. If you can imagine assigning a singular 65,000 host potential network, and you only needed to use 200 of those addresses, you're wasting the other 60,000. And in order to see that very clearly, it does help to maintain and contain the understanding between a binary numbering system and a decimal numbering system, as we describe right there. We then look at the different rules, the different subnet masks, and that allows us to identify the number of bits that we reserve for network space, the number of bits for the host space, and we become much more flexible. We are no longer limited to the /16/24. We can move from /17, /18, /19. And you'll note that when they're using this, they use it as a prefix notation, because what we want that to tell us is which bits are the network bits. And the network bits begin at the left-hand side, moving towards the right. So the first 16 bits, or the first 24 bits, are network bits and that particular designation. And because it is moving from left to right, it's known as a prefix notation, even though that slash value comes at the end of that designation, 192 or 172.16.5.0/24 for that. So that brings us to the end of that particular page. And as we move into our next slide, we take a brief, and I do mean a brief, look at IP version 6. And IP version 6 benefited greatly from our lack of understanding within the realm of IP version 4 and some of the problematic distribution models. First, it's 128 bits in length versus the 32 bits. And that becomes a number that is almost unimaginable. It's 3.4 times 10 to the 38th number of addresses. And in fact, if you got your IP version 6 network, your host addresses would consist of 64 bits. So you have a network that is larger than the entire internet. And with that, they do talk about how we can use all of these numbers and a number of other things within that to really ensure that we're not going to run out of addresses. I kind of think that they could have used a smaller length, but since they chose this, the Internet of Things and all of that demand will continue to fit into that particular structure. And as I note, I only want to add one other thing. I let the time get away from me, and for that I apologize. But the one additional thing that I would like to add is in IP version 6, they integrated the protocol that we know as IPsec. And that ensures that any information exchanged is encrypted from one side to the other. It is inherent within IP version 6 and has been ported back to IP version 4. Most VPNs that we're aware of are IPsec-based VPNs. So while there are benefits, including the expanded size for IP version 6, a number of other things that are beneficial in IP version 6 we're actually making use of, such as the IPsec protocol. I believe this is near to the last page in any case, and I do note that there's a couple of questions down there at the bottom. So our next slide should bring us, well, with a couple of jokes. And I'll leave them up there. I don't even know that I can tell these jokes myself. Raphael says he just lost sound, so I still show my information there, and it could have been from there. Well, maybe it was the jokes, Ronald, that led to that. We do have a couple of questions. I'll see if I can't take as many questions as I can, even though we are a little bit beyond the hour. Hopefully you can hear okay now.
Yep. Lane, I am happy to read these out for you as well here. We can start off with the first one. If a network is misconfigured with two DHCP servers, both handing out the same address range, and a device gets the same IP address as another device on the LAN, how does that affect the network and traffic?
That would detrimentally affect the communication significantly. There was a protocol I didn't mention. The protocol is GARP. It sounds like a joke, but it's not. It's a gratuitous address resolution protocol. And for Windows systems, when they come online, they actually yell out that this is my IP address, this is my MAC. And if somebody says, no, that's my IP address, then both of those devices shut down. They're not communicating on the network because of that problem. But if
Thank,
you did have two with the same thing, that would create a problem.
all
Yes,
right,
yes, it is, Robert.
Thank you, Lane. We have two questions in regards to recordings. Lane, I can take care of these two. The answer is yes. You all will get copies of this recording, and you can expect those in about a week. So those will be on the way. And looks like we have another question here from Joel. TCP window size, what are its units, bytes, segments? How is that determined?
Each device gets to determine what it is sent from the other side. In order for the sender to understand that, the device that wants to receive that information sets the window size. It is measured in bytes with a multiplier. So while you might see the largest number of that being the 65,536, what you will do now is, because we have that, no problem, David. I appreciate that. Joel, it is a multiplier that's used now, so you can have much more functionality than we did in the past. But it is one of the more complex things there. And if there are no other questions, of course, the TCP over IP networking class, networking fundamentals, and a whole series of classes are out there for you to take.
That is correct. If you feel free to visit globalknowledge.com, and as Lane just mentioned, search for the TCP IP networking course. If you would like to continue with today's topic, also, I would feel like I would need to add in, if today's topics and subjects feels like it might be a little bit advanced, we also have a great recommended prerequisite to this course. It's our Understanding Networking Fundamentals course for anybody. And also, if this is a course that you would like to pursue, please take advantage of these promo codes here at checkout, or feel free to call in and present these codes with your sales rep, and they'll be able to assist that as well. And again, that'll be at globalknowledge.com.
And thank you, Chris. Again, I do enjoy doing these things, so please come back anytime.
All right. Thank you, Lane. Thank you all. Hope you all have a great rest of the afternoon.